Go ahead. Thanks, Santi. I'm just going to make sure this does what I think it does. And it does not. Wonderful. All righty. So for those that don't know me, I'm Michael Caplan. I'm a grad student here at Mines in the metallurgy department. And I'm just here to give you all a brief rundown of how we can use hydrometallurgy to process some pyrometallurgical waste products. So with that out of the way, let's get started. Okay, there we go. So most of the seminars I've been to normally start off with the speaker talking a little bit about themselves. So I figured I'd jump on the bandwagon and talk a little bit about me to get going. Will that work? It
won't turn, but it'll later.
Oh, okay. So a little bit about me. I was born in Houston, moved to the Denver area in 2014 for my undergrad. Family's still over there in Houston. I have a dog. He's shown there. He's nicer in pictures. Is a nice way to put it. And I enjoy being outside, like mountain biking, skiing, snowboarding. You know, I cook. I enjoy motorcycles. You know, normal stuff. Video games, Netflix. Education. I got my bachelor's here at Mines in 2018 in metallurgical and materials engineering. I worked a little bit after that, but I pretty quickly came back and got my master's also in metallurgical and materials engineering. And now I'm working on the Ph.D. So you could say I have at least a passing interest in it. I'll talk a little bit more about this later, but my master's project was on critical materials recovery, specifically indium. And right now I'm working on slag reprocessing. So for my professional background, in 2015, I interned for an oil and gas company called Extractive Energy. Most of what I did there was FSRU applications and a little bit of LNG, but mostly regas stuff. I did a lot of plant design, layouts, P&IDs, things like that. And then in 2017 and then a little bit in 2018, I worked for a company called Verite Forensic Engineering. They were a small consulting engineering firm. They did mostly failure analysis and fire investigations. For them, I did mostly metallurgical failure analysis, whatever the plural is. That photo there is basically a photo that kind of shows some of what I worked on. That is an engine block. And for those of y'all that are familiar with engine blocks, you will know that that hole there is not supposed to be there. And there should be a piston in that cylinder. So we can see the valves, we can see the cylinder, we can see the connecting rod. The piston is not there. Long story short, the piston decided it no longer wanted to be in one piece, failed catastrophically, and punched a hole in the engine block on its way out, causing that hole. If you're curious about it, come talk to me after, or we can talk about it for however long you'd like. And then I've also done a little bit on some tailings reuse in 2019. That was a project where we upgraded some silica. And so with that out of the way, let's get down to the meat and potatoes. So this is the mining engineering seminar. I'm not going to pretend to understand to the level that y'all do about how to get things out of the ground. But a little review for what happens once things are out of the ground. So we have extractive metallurgy. So in most commodities, I have copper here as example. There's two general categories. There's pyrometallurgy and hydrometallurgy. And there are exceptions, or other processes. But shown here, I have two general processes for how you might process a copper ore body using pyro and hydro. In pyro, you normally start off with smelting. After that, you would go to converting, which normally just gets rid of iron and converts copper sulfide to a blister copper. From there, you would cast the copper into anodes, which would then be electro-refined. On the hydro side of things, you would leach it, normally with sulfuric acid, but there are other solutions you can use. From there, you would go do some sort of upgrading step. Solvent extraction is most common. After solvent extraction, you have a relatively high-grade copper electrolyte, which you would then refine using electrowinning. So we're going to focus on this left side here. Most of what I do is I use hydrometallurgical techniques on pyrometallurgical byproducts. So that sort of begs the questions, what are the pyrometallurgical byproducts? So a really common one is slag, which is a product of most smelting and converting processes. At least with copper and other commodities, a converter slag is recycled back into the smelter, but that doesn't always happen. Other examples are dusts, which also are the result of most high temperature processes like smelting and converting. Roasting as well will also generate some dusts. Spice is another common example. That is a byproduct from high temperature processes, most notably blast furnaces, especially with lead. And another one is dross. Those normally come from fire refining processes, or they're normally come out as a way to improve the grade of some substance after it's been through some sort of furnace. So with that out of the way, I'm going to start talking a little bit more about some of the things that I've worked on, starting off with recovering indium from smelter dust. And if y'all have some really, deep and important questions about this topic, Joseph Troba here in the audience, he did his Ph.D. on this, so some of those might be best directed to him. So a little bit of background in the overall goal of the project. So this was sponsored by CMI, the Critical Materials Institute, and Rio Tinto, their Kennecott facility specifically. That's located in Utah, right outside of Salt Lake City. So the overall goal was to develop some methodology to economically recover indium from mid and or waste streams in the Rio Tinto circuit. So some more background on Rio Tinto. They can sort of be categorized into sort of four main components. There's the mine. You guys all know what mines do, so I don't have to explain that. There is the concentrator, which takes the ore and does comminution and beneficiation. Beneficiation is done through flotation at Kennecott. The outputs of the concentrator are copper concentrates. Those concentrates get sent to a flash smelter and then to a flash converter. And the anodes that come out of the flash converting system are electrorefined into copper cathodes that are then sold off as a product. So it sort of begs the question, where in this system are we going to get our indium? Well, there's a few things that we can look at. Early on, we looked at some of the samples in the concentrator. If we can improve the grade of indium going into the other downstream processes, that's more indium that we can target later on. We found that that really wasn't going to be feasible for a number of reasons. Primarily, it just wasn't, the indium was not upgraded in specific mineralogies. So it would have been hard to process without some sort of chemical means. We ended up going after indium in the flash smelter. This right here is a flow sheet of it. And what we took it from was the electrostatic precipitator specifically. So what this is so during the smelting process, some of the elements such as indium can become volatilized and will go with the off gases. Additionally, some of the ultrafine particles will just get carried away with the off gases. Because of environmental regulations, these off gases need to be processed. Part of that processing is running them through an electrostatic precipitator, which does a few things. But the big one is it condenses some of the vapors into solids, and all of these solids already present, they're pretty fine. It collects them so that the gas can be processed relatively solid free. So that's the source of indium that we're targeting. And that sort of begs the question, how much indium is there? Well, so right here, we've got some ICP data, and we can see that there's about 50 parts per million of indium right there. Yep, right there. And so what happens to this dust, right? Normally, if we don't do anything with it, ideally, it gets recycled back into the smelter. That's because it's about 20% by mass copper, and Kennecott is a copper facility. So they want to process that copper because it's the primary product, right? But they can't, and that is because of bismuth and arsenic contamination. Both bismuth and arsenic cause problems both in copper production and in the final copper product. On the refining side of things, they cause current efficiency issues and a variety of other things. And in the final copper product, they can reduce conductivity, they can cause some grain boundary wetting, and a variety of other problems. And then also, cadmium is something we want to look at. That's because another target of the project was to produce cadmium telluride, and we need cadmium to do that. So with this material specifically, what are our general goals? Well, one, we want to recover indium, right? It's the primary goal. But we also want to recover that cadmium. We also want to remove bismuth and arsenic because it inhibits copper production. And we also want to preserve the ability to process copper. So, and that's just because copper is the primary product. So whatever we do to this pyrometallurgical dust, we need to do it in a way that the primary economic driver, being copper, can still be the primary economic driver. So what do we do? So we looked at a few things and settled down on water leaching. The reason this worked is there's a pretty high sulfur content in the dust already. And also some of it was copper sulfate. And so what happens when we subject the dust to water is we get some of the sulfur reacting with the water to form some sulfuric acid, not much, but enough to get the job done. And so we get two products from this, a leachate and a residue. The leachate is what the aqueous phase, it's the solution, and the residue is the solid material left behind. So these percentages that I'm showing here, these are recoveries, or the amount of material that reports to each phase. We can see that we're getting, a good chunk, over half of the copper going to the leachate, with about a quarter of the cadmium and not much arsenic. So the leachate is mostly copper. On the residue side of things, pretty much all the indium stays there, most of the cadmium, all of the bismuth, and the majority of the arsenic. And then there's also a good chunk of copper there as well. And so from here, further processing can be done. Joe can talk about this if y'all are interested, so reach out to him later. So this is one of the things that we looked at. Another thing we looked at was doing water leaching first. From here up, it's the exact same as the last slide I showed you. But what we'll do is we'll take this residue and we'll leach it with sulfuric acid. And so the remaining copper goes into solution, along with some of the indium, half of the bismuth, and a good chunk of the arsenic. The residue gets upgraded in indium, and some of the impurities are reduced, and cadmium is still pretty much stays there. One of the benefits of this is the remaining copper gets converted to solution so that it can be processed that way. A downside of this is the bismuth and arsenic go along with it, so that may not necessarily make sense. That said, if you're going to recover the indium, you need to do some sort of processing to this residue anyway. And again, that's what Joe looked at. So on to the next thing. We're going to talk about recovering some constituents from slag, which is what I'm working on right now. And so we are working on slag from La Oroya, which is a metallurgical complex that was operating in Peru. The overall goal of this particular work was to develop methods to process their slag and recover a variety of valuable constituents in that slag. It was sponsored by the Center of Mining Sustainability here and a university in Peru called UNSA. So La Oroya, as I said, it is a metallurgical complex in Peru located there. It started operation in the early 1900s. And it shut down in 2009 for a variety of reasons, most of them environmental. As I talked about, it is a polymetallic facility. Here we've got an aerial view of La Oroya, and the actual facility is shown in that green circle right there, so you can get an idea of the footprint. So like I said, it is a polymetallic facility. And so its primary products were copper, lead, and zinc, but it also produced a fairly high number of byproducts, and those include gold, silver, cadmium, tellurium, bismuth, indium, thallium, arsenic, etc. There's a number of them. And so, like I said, it got shut down in 2009. So why did it get shut down? In large part, environmental problems. So there were two key environmental problems. One is the release of SO2 gas, and the other one was relating to their slag. So the slag pile is shown in the red circle. It's that black spot right there. You can see that in terms of footprint, it's about as large as the actual facility. So the slag created two environmental issues. One says they would release toxic elements into the atmosphere through mechanisms like acid rain. And then also some of the slag particles were pretty fine. So you would get quite a bit of dust pollution into the area. And that causes a variety of issues. So where did the slag come from? Well, they are a polymetallic facility, and two of their primary products are copper and lead. So this particular slag pile is a 60-40 split between copper slag and lead slag. The copper slag is from their copper reverb furnaces, and then the lead slag is from their blast furnaces. So there's about 14 million tons of this stuff. And so that kind of begs the question, what's in the slag? Oh, sorry. This is a side view of the slag pile, just to give you an idea of scale. This photo on the top was taken from about there. And right there, you can see a vehicle that is roughly the size of a Toyota Tacoma. It's actually a Toyota Hilux. And that vehicle is about halfway up the pile, just for reference and get an idea of scale. Right, so what's in this pile, right? There's copper, lead, zinc, and iron are the big components. There's also some trace nickel, some trace gold, and some trace silver. For reference, the gold and silver values shown there, that's at 1,900 an ounce for gold and about 22 an ounce for silver. I haven't checked prices recently, so I don't know how realistic those numbers are right now. But just so y'all know, those are the prices I use to calculate those values. How are we going to process this slag? Well, I've already talked about pyro and hydro, right? So in pyro, there's roasting, fire refining, smelting, and converting, which are some of and smelting was what was used to generate this slag. And on the hydro side, there's leaching, solvent extraction, ion exchange. We could do precipitation or some other sort of precipitation similar process like cementation. But regardless of which route we go with, we can also go with pre-concentration using mineral processing. That would likely involve some sort of flotation or maybe magnetic separation. But sort of these are like the general categories, the tools we can use to process this material. Ideally, we would like to do some sort of pre-concentration with mineral processing. That is going to be a little bit difficult in this case. That's because the slag is amorphous. Which means there's no long-range crystalline structure, which also means there's no long-range order to give us predictable properties that we can take advantage of for mineral processing. So there's two ways we can get around this. One is grind it really, really finely to take advantage of the existence of any potential short-range properties. Alternatively, we could heat it up, get some solid-state diffusion going, and devitrify it or make it crystalline so that there are properties that we can take advantage of on a longer order. So right here, I've got some SEM images, SEM false color images of some of the slag as received after heating at 650 for 2 hours and then furnace cold, and then again at 850. So we can see right here at 650, we are starting to get some devitrification, especially here and here. But this red phase right here is just a different amorphous phase, and I use that term loosely. But it is distinct from the initial phases, being the copper slag and the lead slag here. So we have different amorphous phases here, but we're still pretty amorphous, not crystalline enough for really to be useful for our purposes. So we go up to a higher temperature and we can see that the fine stuff has crystallized pretty well, not completely, but we're happy with it. The coarser stuff, we still have that different amorphous phase that we can see in the 650 samples. So this tells us a few things. One, it tells us that we are getting some devitrification. We are getting some crystallinity in this sample, which is good. That's what we want. But 850 for 2 hours and then furnace cooled, it tells us that vitrification is pretty slow. And we can look at Fick's second law to help us with this. So diffusivity is equal to some intrinsic diffusivity, D naught, multiplied by E to the power of Q, which is some activation energy divided by RT. T is temperature. So what this tells us is that as a function of temperature, diffusivity goes up and asymptotically approaches some maximum based on the intrinsic diffusivity and the activation energy. So what this means is we can only jack up temperature so high and continuously get benefits. We do get diminishing returns when it comes to improving diffusivity as temperature goes up. Also, from a practical perspective, increasing temperature means increasing the cost. So it doesn't necessarily make sense to do this if it's going to be expensive. Another thing we could do is just, melt it and then let it cool down. But at that point, we might as well just go with a pyrometallurgical process. So because of this, we sort of ruled out mineral processing methods and pre-concentration and decided to go straight into leaching. And so we've come up with a general process to do this, and it starts with sulfuric acid leach. From there, we get two products, a leachate and a residue. The copper and zinc form sulfates, which are soluble, and those report to the leachate. The lead also forms a sulfate, but lead sulfate is not soluble, so it remains in the residue. To the leachate, what we're doing is we're neutralizing with sodium hydroxide. You could also use soda ash or any other basic thing, doesn't really matter. And then we're adding some zinc dust to cement out the copper and the iron. And the reason for that is iron causes some problems later on in processing. If we can get it out of the leachate, it just makes it easier. That's due in large part to the multivalency of iron. It makes other processing kind of difficult. So we add some dust to the leachate and we'll cement out the copper and iron. Those cemented solids we can feed into the existing copper pyro circuit, specifically the converting furnace. The iron in the converting furnace is it's not that big a deal. It'll just oxidize off and go to the slag. And then what we're left after cementation is a solution that is basically a zinc electrolyte. The grade of zinc there is higher than the zinc electrolyte La Oroya uses. So we can mix that in with no problem. And so that just goes to the existing zinc electrowinning circuit. The residue, which contains the lead, we are going to subject to WHIMS, or it's a magnetic separation. I forget what it stands for. It's having a moment. And the reason we're doing that is to knock out some of the iron that's in that residue. And so we get two products from the magnetic separation. We get a lead concentrate and an iron-bearing waste. The lead concentrate is still mostly a lead sulfate. And so there's a few things we can do with that, but both involve putting them back into the existing lead pyro circuit. We could feed them in as a bleed stream to their center plant. Or we could make a lead carbonate by mixing in some carbonate and then feeding it to the blast furnace. We're leaning towards the center plant. And then the waste is pretty stable. At this point, anything that can be leached out has been leached out. And so the only issues are realistically dust pollution. And water spray towers make that pretty easy to deal with. So that's the overall process, right? So how do we optimize things, right? So to start off with leaching. So we do our initial tests, get an idea of what's happening. Then we get more data. With additional data, we can create a statistical model. And then that helps us run some statistical analysis. And we can figure out which process variables make a difference and hopefully figure out why. Then from there, we can plug these in. We can plug things into a metallurgical simulation software. And that'll help us with the statistical model to determine some variable effects. So for example, on the statistical side of things, so right here, we have some response services for leaching. So on the left here, we have copper recovery to the leachate, and on the right, silicon recovery to the leachate. Ideally, what we would do is maximize copper recovery while simultaneously minimizing silicon recovery. Excuse me. And so this model can help us figure out the best way to do that. And so a variety of variables go into calculating these surfaces, more than two, but because we're dealing on a 2D surface, we can only show 3 things at a time. So on the z-axis, we have recovery, right? Copper and silicon. And then on the x and y, we have acid concentration and temperature. Other variables that go into making these diagrams are things like temperature, leaching time, agitation. We could do pressure. But the point I'm making is all of those things are calculated into making these things, but we can only display 2 variables at a time, right? And so what we can see is as we increase temperature, copper recovery increases, right? When we go from 25 degrees Celsius to 80 degrees Celsius, we see a slight increase, but it's not all that much. Same thing as we increase sulfuric acid concentration. And, that sort of makes sense intrinsically. More acid, we can dissolve more copper. Revelating, I know. And we can also see that by increasing both simultaneously, we can push up copper recovery even higher, which is what we want to do. On this side, we can see what the effects are for silicon. We can see that by increasing the temperature, we have a slight increase in silicon recovery. And by increasing the acid concentration, we get a decrease in silicon recovery. Now, that is not what you would normally expect if all we're using is sulfuric acid. In the data set used to create this, I also used a strong oxidizer, a hydrogen peroxide. What that does at the higher acid concentrations or at lower pHs, it helps drive some of the silicon out of solution, which basically makes it harder to go into solution, right? You'd surprise. And so what we can see generally is that we can sort of get a min-max, right? So right here, by minimizing silicon recovery, we still get pretty good copper recovery. So basically what we want to do is we want to increase all our acid content. And then from there, we can play around with temperature to figure out what the best break-even point is between maximizing copper recovery and minimizing silicon recovery. And we can follow this line of logic with any of the elements that we're interested in: copper, lead, zinc, what have you, right? And so from there, we can narrow down on some processing conditions that give us, the best combination of recoveries for the goals that we have in mind. And we can do the same thing with cementation. For those that don't know what cementation is, it's basically a heterogeneous precipitation reaction, and it relies on differences in nobility. So if we take a material like copper, which is fairly high on the galvanic series, words. What was I saying? Which is very high on the galvanic series. It's more noble. We can add in a metal that is less noble, like zinc. And what will happen is we'll get a reaction that is based on those differences. Zinc will go into solution and copper will solidify as a solid. The same thing happens with iron. This is why we can use zinc to precipitate out copper and iron in solution. And one thing to note, as I talked about earlier, iron is multivalent, right? And so we have Fe3 plus and Fe2 plus. Ideally, we would like iron to be Fe2 plus. And so what we can do is we can modulate pH and the applied potential to keep iron in the 2+ region so that we can get better iron cementation. So right here, we have the same, response surfaces. We have copper on the left, iron on the right. And this is grade in the solution afterwards. In both cases, we want to do is we want to minimize the grade. We want low copper in solution and low iron in solution because we're trying to take it out of solution so that we can take those elements and feed them in somewhere else while we take that solution and recover the zinc from it, free of copper and iron. And so what we can see in the case of copper is as we increase the amount of zinc dust that we add, we drop more and more copper out of solution. This is pretty much what we expect. And with pH, we can see that as we increase the pH and keep the zinc dust low, we'll get a drop. And the opposite occurs when we keep the zinc dust high. And so on the iron side of things, what we can see is, generally speaking, as we increase the pH, we'll drop more and more iron out of solution. And that for the most part, which is what we expect based on the EHPH diagram. And same thing, as we put in more zinc dust, more iron drops out of solution. This is what we would expect because, right, zinc is what's dropping iron out of solution. Huge surprise. So again, what we can do is we can take these diagrams and help us better inform what sort of processing conditions we want to use to get the results that we want. So it sort of begs the question, right? How do I know that this is going to work? I'm taking some material streams and I'm plugging them into circuits that already exist that I don't really have access to. For practical reasons, I can't really, I can't make them on a smaller scale. They're too complicated and would require too much resources. So what we can do is we can make a model of things, and then we can make a model of things, which is what I talked about earlier. And the software we're using for that is called METSIM. It's a general sort of all-purpose metallurgical processing simulation software. And what we can do with it is simulate pretty much any metallurgical system that we can come up with. So what we do with it generally is, so first we'll model the existing process, the processes that already exist. Then we'll model the new processes. Then we'll take those two models and integrate them together. And then we can see what happens, right? So if we take a stream from the new process and feed it into some unit operation in the old process, we can see where that material goes, what happens to it, and how it affects everything downstream. And we also can figure out what process changes need to be made, right? And what this enables us to do is it enables us to figure out what the potential problems are before things make it to the real world. So we can try and deal with them before things happen. And what that does, it means that if this gets implemented in the real world, theoretically, everything goes smoother. So I just want to thank y'all. I think I kept it to time. I went 3 minutes over. I'm sorry. Alrighty then. Questions?
So I have a question.
Yes.
So we talked about your byproducts being gold and nickel. You don't have that shown in your stream. Where do you recover those? Where do they get recovered?
So they're not things that I'm targeting necessarily. Sorry, I should have spent a little more time on it, but I'm targeting gold, lead, and zinc. Copper, lead, and zinc.
Okay.
Sorry. Targeting copper, lead, and zinc. So realistically, I still need to do the analysis for the precious metals. But if they report to the copper cementation product or the lead, between the two, I think lead is probably a little more likely, at least with silver. They'll end up getting recovered through the existing recovery systems at La Oroya. What happens is in both the copper and the lead circuits, anodes are generated, and those anodes are electro-refined. The slimes from those anodes are what contain the precious metals that get recovered. And so in either case, as long as it goes into those pyro circuits, it'll make it to those anodes and then to the slimes and then get recovered. Yeah.
Did you think about bio-leaching or heat leaching?
We did not think about bio-leaching. Thought a little bit about heat bleaching, but just in the interest of time, didn't do anything with it. But no, we did not consider bio-leaching.
It kind of is heat leaching.
Other question? Yes.
Have you visited the facilities of the Oroya?
Yes, I have. I went there. I actually took the photos that you saw, not the aerial photos, but the other photo.
Have you evaluated if it is possible to integrate this procedure into the existing facilities?
That is a politically charged question. So the question was, how realistic is it that the process that I develop can actually be integrated into the existing processes? So I said that is a political question. The reason for that is There's some political controversy relating to La Oroya shutting down, which means if they get restarted, there would be a political controversy. If they restart, you know, which is an important question, I don't think it would be difficult to integrate the processes. Getting things restarted, though, that's another conversation altogether.
All right, because this facility have problems regarding power and other type of access related things. So,
Yeah, it is pretty remote. Getting things there is kind of difficult.
it's the middle of the main road of the country, so it's definitely not that far away.
In terms of like getting reagents, unless there's a rail there that,
Yeah.
as I understand it, isn't active anymore, at least not to the facility. Oh, it is.
Yeah, it's moving like all the production of the center of the country.
Oh, okay, I didn't know that. When I was there, they told me that they would have to rebuild about a quarter mile to get it to the
No,
facility.
it's like a train going every 5 minutes full of.
Oh, okay.
So,
Oh, I didn't know that.
pretty active.
Okay, no. That's good news. Other questions, comments, concerns?
Thank you.
Alrighty. Can we end this?